Hello and welcome to the Chapter 8 Summary Worksheet from Stevens's Introduction to Statistics, Think and Do. And here we're just going to go over some sort of setup problems first and then entire hypothesis tests on the next 2 pages. And again, it's worth knowing that these answers, as seen here in the instructor's version, are also available in the student version at the back of the book. So you can go over these at your leisure. Okay, so let's get started. We will look at number 1. Let's put it into full screen mode. Okay. For each of the following, state the claim and the null and the alternate hypothesis in symbols. It is claimed that the mean amount of aspartame in Diet Coke is 125 milligrams per 240 milliliters. I'm thinking. Okay, so the claim is that the mean is, and again, is 125. The is just replaced with the equal to sign. The null gets the equal to sign. The alternate, you'd like it to get the claim, but it has to be different from the null, so you're out of luck, and specifically every time you come across a claim of equality, you wind up with the alternate hypothesis of inequality. So this will be a two-tailed test. It is claimed that most of all ice cream eaters prefer chocolate. This is a claim about a proportion, specifically a proportion that is greater than 0.5. So that P is the proportion of all people who prefer chocolate, and we're claiming that that proportion is greater than 0.5, making it most. So that's greater than 0.5. The null gets the equal to sign. The alternate gets the claim because it can while remaining different from the null. For each of the following, find the critical values of Z or T associated with a hypothesis test with the given alternate hypothesis. So I give you the alternate hypothesis, and that'll be sufficient to determine whether it's left, right, or two-tailed test. And then you can determine whether it's Z or T by whether we're using a proportions test or a mean test. Okay, so for the first one, it's a claim about a proportion, so I use Z, the Z table. It is a 0.05 significance level, and it's a right-tailed test, right, because of the greater than sign. So Z table, right-tailed test, significance level 0.05. So I go down here. This is my cheater because 0.05 is one of them. Z table, 0.05, right-tailed test, 1.645. All right, so that's where this comes from. And the next one, it's about a proportion, so I know to use Z. There's a not equal to sign, so it's a two-tailed test. And the significance level again is 0.05. So I go to the Z table. 0.05, it's now a two-tailed test, so it's plus or minus 1.96. That's where that came from. Now for the next two, I have a claim about a mean, so this is going to be a t-test. Mu, which means I'm going to use the t-table, less than, so it's a left-tailed test. The significance level is 0.01. My sample size is 35, so my degrees of freedom is 34. So degrees of freedom, 34. Left-tailed test, 0.01. Okay, let's see if I can remember all that. So it was a one-tailed test, a left, at the 0.01. So I'm in the second column. All right. Degrees of freedom was 34. So 2.441. But it was a left-tailed test, so I got to stick a negative in there, right? Negative 2.441. Well, that's where that came from. So again, I have a test about a mean. So I'm going to be using the t-table. again, is a left-tailed test. So I'm going to be using the negative of what I find in the table. N is 105. Alpha is 0.01. So now the degrees of freedom is 104. Right. Same thing, left-tailed 0.01, degrees of freedom 104. So I'm over in this, certainly in the second table. So it's a one-tailed left 0.01. Okay, so my degrees, so I'm in the second column, I know that. And I'm looking for 104 as my degrees of freedom. And as you can see, it's not in there. Now 105 is closest, but that's not actually the way we play this game. And so if your degrees of freedom isn't here, you can look up here. It tells you what to do. If your degrees of freedom is not in the table, use the closest lower value. So that means I'm going to use 100. So my critical value is 2.364, but this is a left-tailed test, so it's going to be a negative. Right, negative 2.364. So that's where that came from. Right. Okay, critical values, good. Now we're going to find some test statistics, and this is just basically, can you use your calculator accurately? But the claim is going to be that P is greater than 0.6, sample size is 36, P hat is 0.7. So knowing that it's a claim about a proportion, I know that I'm in chapter 8.2, and my test statistic is given by this formula. So I need P hat over P, and P comes from the null hypothesis, which I don't have here, but look, if my claim is that P is greater than 0.6, then my null hypothesis is going to be that P equals 0.6. So P is 0.6, making Q 0.4. So P hat, P again, 1 minus P for Q, divided by N is 36. And if you plug all that into your calculator accurately, you get 1.22. So now I'm talking about a claim about a mean. The claim is that mu does not equal 7.2. But regardless, the null will always have that the mean, there's always going to be an equal to sign there. N is 121, X bar is 6.8, sample standard deviation is 2. Since I know it's about a claim and I don't know sigma, I'm talking about chapter 8.3, where my test statistic has this formula. X bar, 6.8. Mu comes from the null hypothesis, 7.2. Sample standard deviation is 2. Sample size is 121. And if you plug all that into your calculator accurately, you get a test statistic of negative 2.2. Now we're going to calculate some p-values. Given the alternate hypothesis and test statistic, find the p-value of the test statistic. So H1 is that the population proportion of some kind is less than 0.25. So specifically, this is a left-tailed test. All right, and my test statistic is negative 1.85. So if I'll just do a little graph over here. Negative 1.85. So my p-value is the probability of getting a z-score more extreme, and in a left-tailed sense, that's to the left of negative 1.85. So that's my p-value, is the area of that tail. So I just look up negative 1.85 in the table, and that gives me that area in that tail. I'm going to go back to my z table. Long way away, lots of scrolling, don't get dizzy, almost there. I think I forgot what the value was. I think it was negative 1.85, right? So there's negative 1.8. And then 5 comes from here, so it is 0.0322. So that's that area in that tail. 0.0322. Right. Okay, for the second one, here I have a two-tailed test. because the alternate hypothesis has a not equal to sign. So if I draw my picture here, I'm going to make it very flat and have to interfere. It's two tails. I get a test statistic, same thing, negative 1.85. So anything to the left of that is in the rejection region. But because it's a two-tailed test, anything bigger than positive 1.85 is also going to be in the rejection region. So I have not going to be in the rejection region. Sorry, is also going to be more extreme than 1.85. So more extreme than negative 1.85 in a two-tailed sense is less than negative 1.85 or greater than positive 1.85. So I need the combined area of these two tails. But we just found the area in here. That was what we did in the last problem. So that is 0.0322. So that means this one over here is going to be 0.0322. So we just double the p-value from the last problem to get 0.0644. A couple of questions about significance level. Suppose a null hypothesis is rejected at the 0.05 significance level. Will it gotta get rid of this. Will it necessarily be rejected at the 0.01? Why or why not? Well, the answer is not necessarily, and here's why. Suppose you had a p-value of 0.03. It would be rejected at the 0.05 significance. The null hypothesis would be rejected at the 0.05 significance level because 0.03 is smaller than 0.05. But it would not be rejected at the 0.01. Not rejected because it is larger than 0.01. So if it is rejected at 0.05, it is not necessarily rejected at 0.01. And the next problem says, if it is rejected at the 0.01 significance level, will it necessarily be rejected at the 0.05? Well, look, the null hypothesis will be rejected at the 0.01 significance level only if the p-value is less than 0.01. But if the p-value is less than 0.01, it certainly is going to be less than 0.05. So if it's rejected at the 0.01 significance level, it will necessarily be rejected at the 0.05 significance level. All right, let's do a couple tests here. In a study of 600 randomly selected car crashes, it was found that 315, or 52.5% of them occurred within 5 miles of home. Use a 0.05 significance level to test the claim that most car crashes occur within 5 miles of home. Now, the problem that most students have with this is they see that 5 miles of home and they want to do some sort of like mu is less than 5. But the claim isn't about a mean. It's about a proportion. It's saying most, right? So I'm going to let P represent the proportion of all car crashes that occur within 5 miles of home. Right? And I'm claiming that P is greater than 0.5. In other words, most of these car crashes occur within 5 miles of home. The null gets the equal to sign. The alternate gets the claim. My test statistic for a population proportion problem is p hat minus p over the square root of pq over n. There's p hat. All right, p hat is 52.5%, which is 0.525. So that's p hat. P comes from the null hypothesis, 0.5. There's p, 1 minus p is q, divided by a sample size of 600 gives you 1.22. So we want to just make our decision about the null hypothesis, reject or fail to reject. So if we use the critical value method, this is a 0.05 significance level. It is a right-tailed test because of this. That greater than sign in the alternate hypothesis tells me it's right-tailed. So 0.05 right-tailed z-table is going to be found right down here. 0.05 right-tailed, 1.645. So there's my critical value. Rejection region is everything to the right. My test statistic 1.22 is not in the rejection region, so I fail to reject the null hypothesis. I can also get the p-value, which is the probability of getting a z-score more extreme than 1.22, and in a right-tailed test sense, more extreme is bigger. So if I look up 1.22 in the table, in the z table, it's a positive 1.22. 1.2, it's 0.8888, but that's not the p-value, that's this area over here, so 1 minus that is 0.1112, and here the p-value is bigger than alpha, so again we fail to reject. Either one will get us there. So we failed to reject the null, so if our claim is that p is greater than 0.5, right, and our null is the p equals, we can't reject this, so that's not good for our claim. There is not enough, well, there's not enough data to support the claim that most car crashes occur within 5 miles of home. Right. Let's take a look at this alteration. Suppose instead of 600 it had been 6,000. Right? Would that change the conclusion? Well, it's certainly going to change your test statistic because now n is 6,000. That in there becomes 6,000. It does change things dramatically. 3.37 is much bigger, right? And specifically, it is deep in the rejection region. Right? Our rejection region is 1.645 and above, so I'm definitely in the rejection region. So we're going to reject the null hypothesis. And you can also check the p-value. The p-value is 0.0001, which is now smaller than alpha. So at this point, we would reject the null hypothesis and conclude that there's a sufficient amount of data to support the claim that most car accidents occur within 5 miles of home. So the sample size plays a big part in your test statistic. All right, so we're back to our speed limit monitoring device. And now this is a test about a mean, right? The speed limit monitoring device on West Street is used to inform drivers how fast they are going. I watch it for a little while, and I see that from a sample of 40 cars, the mean is 31.1 miles an hour with a standard deviation of 6.2. That's a sample mean. We're going to use a 0.05 significance level to test the claim that the mean speed of all drivers on West Street is more than 5 miles an hour above the posted speed limit. Now, we did this problem in Chapter 8.4. If you did Chapter 8.4, a lot of professors will skip that section. But in that section, we assumed that we knew the population standard deviation. Now we're actually treating this in a more realistic fashion where we have the sample standard deviation. So this comes from Chapter 8.3, tests about population means, where sigma is not known. And we're basically claiming that the mean speed of all drivers on West Street is more than 5 miles an hour above the speed limit. So what we're claiming is that mu, the mean speed of all drivers, is greater than 30. The null gets the equal to sign. The alternate supports the claim because it can without being the same as the null. So there is my test statistic from Chapter 8.3. X bar comes from my sample. That was 31.1 right there. My standard deviation, S, is 6.2. That's right here. And my sample size was 40. So I plug all those into my formula for the test statistic. I get 1.12. It's kind of small. I'm not looking good for my test statistic there. Or it's not looking good for my claim. Conclusion regarding the null hypothesis and why. Let's do the critical method first. When we look for the critical values for a one-tailed test, right? It is a right-tailed test. Degrees of freedom is 39, right? Degrees of freedom is the sample size, 40 minus 1. Right? So, one tail, bright tail, 0.05 degrees of freedom is 39. But notice, by the way, this is very important. The test statistic is a t, so I'm actually going to the t table, right? 39.05, one tail. So, it is a one-tail test at the 0.05 significance level. So I'm in the fourth column there, or the second to last, depending on where you start counting columns. One tail, 0.05 right tail, so it's the positive, and my degrees of freedom was 39, right? Let me get rid of these. It was 1.685. It was a right tail test, so I don't have to give it a minus or a plus or minus or anything like that. 1.685, my rejection region is everything to the right. My test statistic is not in the rejection region. Not in the rejection region, so I failed to reject the null hypothesis. If you have software, you get a p-value of 0.134, which is bigger than the significance level, so again, you failed to reject the null hypothesis. So again, we don't have enough data to support the claim. There's not enough data to support the claim that the mean speed of all drivers on West Street is more than 5 miles an hour above the posted speed limit of 25. Right, so the claim about all drivers, clearly the mean from my sample was greater than 30, but it wasn't far enough above 30 for me to make the conclusion about the mean speed for all drivers. So here's a little thing. Don't let all of this interfere with common sense. And here's what I mean. Suppose a group of students want to test the claim that college students average more than 40 hours per week doing out-of-class work. So they claim that mu is greater than 40. Right? They randomly survey 100 college students and find the mean out-of-class time is 35.5. X bar is 35.5. Is it necessary to conduct a formal hypothesis test on their claim? And the short answer is no, right? Because you're claiming that the population mean is greater than 40, but your sample mean is less than 40. So you should drop that claim right away. You might be able to claim that mu is greater than 35 because your sample mean is greater than 35. But what would if you proceeded with this, things would get really weird pretty quickly. Because your test statistic would be, t sub x bar would be x bar minus mu over s over the square root of n. But x bar is smaller, so this would be a negative. You get a negative value, but you'd be doing a right-tailed test. So what that means is your t would be over here, but you'd be doing a right-tailed test, so the p-value would be huge. The p-value would be bigger than 0.5. And so you get all things would get mixed up. You'd have negatives where you should have positives, positive p-values that are huge. And the idea is this: you're never going to support a claim about a population mean that isn't at least somewhat supported by your sample mean. Right? The sample mean has to give you good reason to believe this claim. If you claim that mu is greater than 40, but then you get x bar of 35.5, you can drop your claim right there. Maybe come up with another claim or something. So don't let this interfere with common sense, because there's a lot of stuff going on, but it shouldn't have you thinking that you might be able to support a claim where the mean is greater than 40 when your sample mean was less than that value. All right, so that is the end of the Chapter 8 single sample hypothesis testing. If you're still with me, I'll see you in Chapter 9, I guess. All right, have a good day.